This is the second part of our discussion on the concept of limit of complex valued functions. So far we have learned why we need concept of limit to understand the behavior of complex valued functions. And we also, using some simple observation, we also agreed on a precise mathematical definition of limit of a complex valued function. So if we are given a complex valued function f, then the limit as z approaches to z0 is equal to this number L if for every epsilon greater than 0 there exists a delta greater than 0 such that the distance between the functional value is less than epsilon whenever the distance between z and z0 is less than delta. Now in other words, it means that whenever z is approaching to z0, then the functional values f of z, they are approaching to this complex number L. Now there is a problem with this definition, that it is not a very convenient to apply. It is not very easy to apply and check the value of a limit of a function. So our next aim is to provide a practical method for computing limits. Now what is that practical method? So we want to use connection between complex valued function limit and the limit of real valued function. Now what is that connection? Let's have a look at that connection first. Now we know that a complex valued function can be written in the following form: u of xy plus iota v of xy. Now this u of xy is a real valued function, and this v of xy is another real valued function. But now these two functions are functions of two variables, x and y. Okay. Now we want to find the relation between the limit of this complex valued function f of z and the limits of these two multivariable functions, because there are more than one variables, in fact two variables, so these are multivariable real valued functions. Now what is the main motivation of this connection? So the main motivation is this theorem that we will be proving in our next discussions. So this theorem states a very precise connection between the limit of a complex valued function and the limit of these multivariable functions u and v. In fact, the result says that if we want to calculate this limit, then it is logically equivalent to calculating these two separate limits. And these two limits are in fact limits of real valued functions. So that's why we want to understand what does this limit mean. In other words, what does the limit of multivariable real valued function means. Okay. So in other words, we want to understand this limit. Okay. Of course, we will restrict ourselves to a function of two variables. Okay. Now this limit, of course, we know that what does limit mean. So the limit means that whenever xy approaches to this point x0 y0, then the functional values u of xy approaches to u0. So in other words, we can say that the functional values u of xy, they can be made as close as we want to the value u0 by taking xy to be sufficiently close to x0 y0. Okay, so in other words, whenever we are approaching this point x0 y0, then the functional values are extremely close. Okay, so as close as we want to this value u0. Okay, so to understand it geometrically, we know that this function u of xy, so it can be considered, or it can be associated to a surface in three-dimensional space. So how do we associate it? Now, what is the domain of this u of xy? So the domain is going to be some subset of xy plane, because there are two coordinates x and y. So the domain of this function is going to be, let's say this D, it's a subset of xy plane. Now, corresponding to each point of this domain, we can find the functional value and we can plot it along z-axis. Okay, so for example, this is a point in the domain and we can find its functional value at that point, and then we have a point in three-dimensional space where the xy coordinates are the same as the xy coordinates of this point of the domain, but the z coordinate is in fact the functional value at that particular point. And similarly, we can find the functional value at any other point. So let's say consider this point, and at this point we can find the functional value, and we can plot it to be another point in this three-dimensional space. Now, if we can find the images at each and every point of the domain, and we connect all the points which we got after applying this function u of xy, then after joining all of these points, or the collection of all of these points, will form a kind of surface in three-dimensional space. Now, what does this limit mean? So this limit means that whenever we are getting closer and closer to this point x0, y0, then the functional values are getting closer and closer to u0. In other words, the distance between u of xy and u0 is getting smaller and smaller. Okay, so in this picture, so let's say this is L. Okay, so let's say this is L. So in this picture, we can say that the functional values are getting closer and closer to this number u0. In other words, if we say that are the values closer than 0.1, then the answer should be yes. And if we say that the values are closer than 0.0001, then the answer should be yes. In fact, we can choose any epsilon, and we can say that, okay, the functional values are closer than this arbitrary real number epsilon, and if the answer is yes, then we say that the limit is equal to u0. So in other words, whenever we are getting closer and closer to this number x0, y0, okay, so this should be x0, y0. So whenever we are getting closer and closer to this point, then the functional values, which are of course the output of this is a real number, so these real numbers are getting closer and closer to this value. Okay, so the limit is L, so this is in fact u0. And of course, when we say that the points are getting closer and closer to this point x0, y0, in other words, since these are points in the two-dimensional space, we can say that the distance between x0, y0 and any other point xy is getting smaller and smaller. Okay. Now, what does it mean geometrically? It means that let's say this brown, light brown is the surface, is the graph of this function u of xy, and we want to see that if the distance between functional values and u0 is less than some prescribed value epsilon. In other words, we want to see that if there is some points in the domain such that all the functional values corresponding to those points lies between these two blue sheets. Okay, so these two blue sheets are basically describing the epsilon distance along z-axis. Okay, so if we say that the functional values are less than epsilon away from u0, in other words, we want to say that the functional values lies between these two sheets, and we can see that for the values inside this small circle, which is a subset of the domain, all the functional values lies between these two blue sheets. And of course, if we vary epsilon and if we can find some subset of the domain corresponding to every epsilon, then we say that this is the limit. Okay, so more precisely, this distance u of xy minus u0 can be made arbitrarily small by making the distance between xy and x0, y0 small. And more precisely, we can say that this distance is getting smaller and smaller when this distance is getting smaller and smaller. Okay. Now we have the precise definition, and this is the epsilon that we choose to observe that, okay, corresponding to this epsilon, the functional values are closer than this. So for each epsilon, we should have this delta, okay, such that the distance between functional values is less than epsilon whenever we are in the delta neighborhood of x0, y0. In other words, whenever we are inside this small disk, this small open disk, in other words, the center is x0, y0, and set of all points whose distance from x0, y0 is less than delta, in other words, this open disk. So whenever we are inside this disk, the distance between functional values and u0 is less than epsilon. Okay, let's have a look at some example. We have a function and we want to check whether this limit is equal to 0 or not. So to calculate this limit, we use polar coordinates and we use the expression x is equal to r cosine theta and y is equal to r sine theta. And using this substitution, let's see what will be the form of the function. So the function becomes, after replacing x with r cos theta and y with r sine theta, we get the following expression: 2r cube cosine cube theta divided by r square cosine square theta plus r square sine square theta. Now after simplification and using the fact that cosine square theta plus sine square theta is equal to 1 and cancelling out this r square with this r cube, we get the following expression: 2r cosine cube theta. Now what do we want to prove? So we want to prove that the limit of this function is 0. In other words, we want to check whether this distance is as small as we want. Now using this polar coordinates, okay, so in polar coordinates, so we can say that in polar, this distance becomes 2r cosine cube theta, and which is of course equal to 2r cosine cube theta. And we know that cosine cube theta is less than or equal to 1, so we can say that this is less than or equal to 2r. Now if we want to prove that this distance, the distance between u and 0 is less than epsilon, it will be very sufficient to prove that this 2r is less than epsilon, because this 2r is a bigger number than this distance. So if we can prove that this 2r is less than epsilon, then of course we'll be able to, so it will be sufficient to prove that this distance is less than epsilon. So in other words, 2r is less than epsilon implies r should be less than epsilon by 2. So we have this expression and we are going to use this expression to prove this limit. Now on the other side, corresponding to this epsilon, we need to find this delta greater than 0 such that u of xy minus 0 is less than epsilon. So in other words, we want to prove that, okay, so find delta greater than 0 such that u of xy minus 0, which is less than or equal to 2r, is less than epsilon whenever the distance between xy and 0, 0. Okay, so the distance between xy and 0, 0 is x minus 0 square plus y minus 0 square is less than delta. So we need to find this delta. Now this expression is in fact r. Okay, so we can say that we need to find delta such that this distance, which is less than or equal to 2r, is less than epsilon. So whenever r is less than delta. Now using the observation that if r is less than epsilon by 2, then this expression holds. We can choose delta to be epsilon by 2. And using this value of delta, whenever delta is equal to epsilon by 2, then of course r will be, okay, so this implies r is less than epsilon by 2 implies 2r is less than epsilon. So this implies this, and this implies the distance between u and 0 is less than epsilon. So that's why if we choose the value of delta to be epsilon by 2, then we can easily show that the limit of this function u of xy is in fact 0. Now the value u naught of the limit must not depend on how we approach this point x naught y naught. So when we say approaching, it means if we choose a path in the domain of the function and we move along that path to reach this point x naught y naught, then this corresponds to a path on the graph of this function u of xy, and in fact we are approaching this value along this path. And if the limit is in fact L, then it should not matter which path we are choosing, and each time we will be approaching at the same point. Okay, so in other words, this gives us another way to prove that the limit does not exist, because there are in fact infinitely many paths, so it is impossible to implement this definition or this criteria to check whether the limit exists. But it can only be used to show that the limit does not exist, because if you can find two paths and along those two paths the limit of the function is different, then we say that the limit does not exist. Let's apply this approach to this function. Now in this case our function is xy over x square plus y square, and we want to calculate the limit when xy approaches to 0, 0. And the path given is y is equal to x. So in other words, limit xy approaches to 0, 0 of xy over x square plus y square. And if we just write it over here, just for a reminder, along y is equal to x. And if it is along y is equal to x, then it becomes a limit. So y is equal to x means, so it becomes x, x. Okay, so y is x. So we can just replace y with x, so it becomes x square over x square plus x square. And this is the same as limit x approaches to 0, x square over 2x square. And of course we can cancel out x square over x square, because x is not equal to 0, it is in fact approaching to 0. If it is equal to 0, then we cannot cancel out 0 with 0, so it is in fact equal to 1 by 2. Now let's see what is happening graphically. So this is the graph of the function u of xy, and if we are saying that we are calculating the limit of this function while we are approaching origin 0, 0 along the path y is equal to x, it means that we are traveling along this line, this black line, and this central point is basically the origin. Okay, so now you can see that there is a gap in the graph of the function. So in fact the functional value is somewhere over there and not over here. But since we are calculating the limit and not the functional value, so that's why we are getting a different value than a functional value. So the limit in this case is in fact 1 by 2. Now we can calculate the limit along the other line, which is y is equal to minus x, and in this case on the same lines we can see that xy approaching to 0, 0, it means xy over x square plus y square, and this is in fact of course along y is equal to minus x. And using the same observations we can say that it is equal to limit x approaches to 0, and then in this case since y is equal to minus x, so we are getting minus x square over x square plus y square, and sorry, this y square is x square, so this becomes x approaches to 0 minus x square, so this y square is in fact x square over 2x square. So once again we can cancel out, and the value of the limit in this case we can easily see that it is going to be minus 1 by 2. Now let's see geometrically what is happening. So once again this is the graph of the function, and if we are calculating the limit along the line y is equal to x, now you can see a black line which is the line y is equal to x. Now when we are moving on the graph of the function along this line, so since there is a gap over here, so we are approaching a point which is below the point which we calculated in the earlier case, which is y is equal to x case. So in this case the limit of the function while approaching or moving along y is equal to x is this number which is below this number. And if we move this line again and again, in fact we are changing the path along which we are moving, and if we approach this line, now you can see that along this line the value of the limit is different than the value of the limit along y is equal to x. So in this discussion we learned a relation between the limits of complex valued functions and the limits of real valued functions. So the proof of this theorem, which is our main motivation for this discussion, is going to be part of our next discussions.